All right, I think I'm gonna get slowly started. So good morning, everyone. So today, the second part of my lecture, and basically I will transition today from the heat wave to taking photos of particles and ideally of dark matter. There will be still a little bit of overlap between those two today. So in general, semiconductor is the key point here. And then the question is, how we measure heat. I discussed this very broadly yesterday, and also Paolo described it, and today I will transition how to measure the charges. So yesterday I just mentioned that charges are also being produced and you can pick them up, but today the focus is more on what do we want to learn from the charges, why do we want to measure them, and how do we measure them best. And for this version, so again, I showed you yesterday this picture and saying that direct detection is really much more than the traditional dark matter nucleon scattering. And in this lecture today, we actually keep this plot false. I'm not removing any of the interactions, because when you I mentioned that today we are more interested in the electron. So all those interactions that also generate electrons are, not generating electrons, but moving electrons. So when they're transferring energy or momentum to the electron. So the electron is the one that picks up the information from the dark matter. So all these processes where this is the case, they will be shortly highlighted today. And in a way, this entire lecture, so this part 2 is, yesterday was very deep into experiment and like tiny devices of the experiment in great detail. Today is more at, the title of the whole school is where theory meets experiment. And so this lecture today is much closer at that interface. So it's a little less deep in the experiment. It's clearly also not a theory presentation, because I'm not a theorist, but we speak with each other, right? And so sometimes we have to find a common ground and exchange and just see, okay, where can we get together in order to broaden the picture on both ends? So how can we make more out of the detectors that we have? And from the experiment side and from the theory side, how can we exploit more of the data that is there? So this is the lecture today, or this morning. And this also then to say that on this mass beam where we are, so I mentioned I am really on the particle part, so I'm not doing any wave detection, but also the particle detection. So the thermal candidates, so those that have been in thermal equilibrium with the universe at some point in its evolution, they are somewhat restricted at around the kV scale. So they are fermions. In the end, if they're getting too small, their density is getting too high, and you cannot really put them in the small in the halos anymore that we have because of Fermi pressure. So here there is a certain intrinsic bound. But if we go then from fermions to bosons, we can go to much lower masses, so this means we can have a much higher number density. That's fine. At some point, again, we are more like in the wave regime, but there's this regime down to something like EV scale where particle detection still works. And so today, the experiment, so I started yesterday with super CDMS, mostly, but today there's also a transition to other experiments showing you how they can probe EV scale, EV to kV scale bosonic dark matter. But in all cases, so this is still about, what I still call the low mass challenge, because in the end, it's about low masses. And the original start that we did was with the dark matter nucleoscattering. And just as a reminder, the challenge was to get this tiny, so the masses get smaller compared to your nucleus, so the recoil energy gets smaller. And so if you want to probe lower and lower masses, we have to come up with strategies. And what I discussed yesterday is one strategy is to lower your threshold of the detection and to also pick up those tiny recoils. But today it is about, and actually one thing I didn't manage to show yesterday because I was running out of time. So at the lowering the threshold, I just wanted to show you right now the world leading result is standing, and this is with Tesseract. So a reminder, also Tesseract, the silicon device that I discussed, works from a principle very similar to Supercilium S. So it's a spin-off of Supercilium S. And I just want to point out, so this is the reconstructed energy. Just ignore this part for now. This is a reconstructed energy, and you see that we are here on the EV scale of energy. So this is really, really tiny energies that we are able to get at this point. And when you're wondering in terms of what we mean with tiny energy. So I just, 2 days ago, I haven't calculated it myself, but I just had this discussion. I haven't checked whether the calculation is correct, but I trust my colleagues. We were just standing together over a coffee break. And he said, so when he was trying to make an analogon for like macroscopic sizes, what a keV recoil energy, the scale when you have a bacterium and let it drop on the ground. Then you have a keV scale energy transfer. So just to give you an idea of what scales we are talking about, and this is now EV scale. So it's really tiny energies that are being transferred. And with these tiny energies, so you can see here, what is in here is different potential dark matter models. When you try to fit them, you get the constraint, how much of dark matter is in agreement with your data, so how much dark matter could be hidden in there. And you see these are going down all the way to sub 100 MeV mass. So this is 100 MeV, this is 63 masses. So the Tesseract is seeing the recoil shoulder of sub 100 MeV dark matter. And this is what you see here then on the x-axis, the mass, here the cross-section, and it's going all the way here. And this part actually I mentioned already with the shielding to be taken into account. But I just really wanted to point out that what we are talking about here is in terms of energy resolution is about 400 millieV energy resolution. So this is just for the low mass challenge in dark matter nuclear scattering. This is really, really a difference compared to just a couple of years ago still. So the other thing, and this is actually what today is about. So yesterday was lowering the threshold. Another alternative is just use the detectors that we have already and exploit other interaction channels. So maybe there are interaction channels that are valid in the dark matter model that are more beneficial to probe. And the ones that I want to talk about is Bremsstrahlung, and so in quotes, because it's not truly Bremsstrahlung, the Migdal effect, dark matter electron scattering, and then the bosonic absorption and bosonic scattering. And I'm putting this in parentheses because on the left-hand side, I'm showing you WIMP mass over WIMP nucleon cross-section. These two, actually, this should also be in parentheses, but these two are probing this parameter space. This one is actually probing in different parameter space, but at least the same dark matter model. And this one is, probing an entire different dark matter model. So when I'm saying exploiting alternate interaction channels, it partially means also moving away from this parameter space. So let's get there. And so just maybe as a heads up when you see results, so like this. So here's a very nice compilation that came out last year, and where Jure was involved. And it's actually, if you haven't seen it yet, you should take a look. Keep in mind it's 515 pages, so it's not really an article, it's a book. And it's really nice. It has a very comprehensive overview over where the field stands as of 2024. And I took these pictures from that compilation, and you see here on the x-axis is all the dark matter we've been talking about so far, so the thermal candidates. On the y-axis we have now spin-independent, cross-section spin-dependent, neutron spin-dependent proton. And what I want to point out, so since this is about low masses, so light dark matter, this is at around 1 GeV. That's what I introduced yesterday. And so you can see that there's actually quite some activity below 1 GeV. And yesterday I made all this effort about explaining to you, Supercilium S, Tesseract. And what you see here instead is there's xenon showing up. dark side showing up. So there are actually those other experiments as well that are typically at the higher masses. And the point is that here you need to be careful. Not all of it is elastic scattering. So what I showed you yesterday is the standard elastic dark matter nuclear scattering. Here, when you look in more detail, all of these, so just sticking with this spin independent, all of these here below the 1 GeV, so Sensei at SNOLAB, Migdal. This work here, Migdal. Then here, the xenon work, Migdal. This is all showing basically dark side Migdal effect. So all of these that are below the 1 GeV range on this plot are actually exploiting the Migdal effect. So you have to read the fine print. It's to make sure that what you're actually looking at is on the same footing. And this is basically the motivation where I want to go. So, coming back here, apparently this seems to be helping that you actually get for experiments that are normally sticking here with xenon that are normally in a GeV to TeV range. It seems to give them access also to the sub GeV regime. So that's the motivation why I want to discuss this in a little bit more detail. And in a way, this is not. I'm not explaining you how the experiment works because you've learned how a xenon TPC works. I've discussed super CDMS. I will discuss Sensei and Damic a little bit today. But in principle, this is now more about those interaction channels. And let me start with one that is not so often mentioned, is the, again, quote unquote, Bremsstrahlung. So it's what I mean, or what people mean when they are referring to Bremsstrahlung, is really that you have either final state radiation or initial state radiation radiating off your nucleus. And instead of measuring the recoil itself, so first of all, then you have not only the recoiling nucleus, but you also have a photon that you can measure. And when you now look at the rate, you have the differential rate over energy. And your the elastic scattering. So let's just pick one. Let's pick green for xenon. Of course, it's different for the different nuclei. Xenon is the heaviest. So for a given dark matter mass, 1 GeV, xenon gets the lowest maximum recoil energy, again, because of just the kinematics. For the lighter nuclei, you have higher maximum energy. And you also get the initial final state radiation, so the photon that you can measure. And that photon, it has a lower rate. It's much more rarely than the elastic recoil itself. However, since we're in a bound system, there's energy stored basically in an atom, and you get extra energy if this is being released, and the photon really goes all the way. So we are here, that is kV, so this is 100 eV-ish. The photon goes all the way up to 3 kV in this. And so if xenon, for example, has a threshold here, you will never be able to see the elastic recoil. However, you can see the photons. Really, the goal here is to observe the photon as opposed to recoil. I mean, the moment the recoil is above the threshold, you check for that. But this effect is what gives you access to dark matter masses that would otherwise be below your threshold. Now, just because you're always being told when you see these plots and there are features, you should ask, okay, what are these features? And you see that there's a lot of stuff going on. And I don't want to go in the detail really of this this equation, but this is the differential cross section. Here is the elastic parts, the spin-independent elastic scattering, and then you have this additional factor in there. And within this factor, so it's really just the atomic scattering function. And again, I mentioned already an anti-atom is involved. And so you have to keep the atomic structure in mind, or have to take this into account. And part of this scattering function, and so both in the real and in the imaginary term, you have the photoelectric cross-section. So basically what you're seeing here, so these features are well known from the photoelectric cross-section, where you're basically reaching the next level of your electron. So this is what these features are about. So it's really, again, just the atomic structure or the electron levels that you need to take into account. And then where does it put you? So I'm showing here, these results are oldish by now, 2019, but I'm showing them because PandaX actually did the Bremsstrahlung and also SuperCMS generated a Bremsstrahlung limit. And you can see the elastic scattering limit is here at the 10-ish GeV range. And of course, the sensitivity is much better because the rate of the elastic scattering is much higher. But at some point, the recoil shoulder is below the threshold, but the Bremsstrahlung gives them access at a lower sensitivity, but pushing down to lower masses. And another thing that you need to take into account when you see in these plots, often you have something, a little bit extra in here. And this is also a little bit new to direct detection. I mentioned yesterday that if you are with accelerators or with collider physics, it's very model dependent. So whatever, when you're going onto this parameter space, it's always important what kind of mediator do you actually have. So what coupling are you really probing? How is the mass of the mediator related to the mass of the dark matter? We're now in a regime where this also starts to matter. And so basically you have here also a dark matter form factor inside. And the dark matter form factor depends on the mass of your mediator. If you have a very heavy mediator, their interaction is basically point-like and your form factor gets to 1. If you have an ultralight mediator, you have the suppression term where Q is the momentum transfer and here the mass of the mediator. So this is just a small detail that in these processes, so whenever we are probing this and presenting our results, we need to explain which cross-section we are probing, whether it's for a heavy mediator, or ultralight, or anything in between. I mean, those are the benchmark models, and this is what you normally see here then in the corner of this plot. Now that's the Bremsstrahlung, and now the question could be, why don't we see that that often, but much more the Migdal effect? And before coming to the Migdal effect, let me just briefly remind you of what it is. So basically, so first of all, the Migdal effect originally has nothing to do with dark matter. It's a process that is being predicted for a classical for the standard model picture. And I'm just drawing it for dark matter because that's what we are interested in, or not even I'm drawing it, I'm and again, stealing the picture from Ured als compilation. And the point is that you have a particle coming in, scattering off the nucleus. The nucleus is sitting in its electron cloud, and there's a certain latency. So there's a certain inertia, let's say, of the electron cloud. And the recoil is moving. The electron cloud hasn't noticed it yet. So it's again, there's this small delay in the response. And then the electron cloud is following the recoil, where, for example, if you have an electron, there's a certain probability that not all electrons are falling, but effectively one electron is being emitted. And the goal here is then, of course, similar to the Bremsstrahlung, instead of trying to observe the recoil, you're trying to observe the ejected electron. And the picture is very similar. So we have here the recoil energy, here the differential rate, and again, the elastic nuclear part. So this is in this case now for germanium. And you have here the elastic nuclear recoil, and then the Bremsstrahlung we just talked about. And you see that for the Migdal effect, the Migdal electron has the same energy range, but a much higher rate. So the probability for this to happen is higher than for a Bremsstrahlung to happen. And this is the same argument. First of all, if you have an analysis threshold or energy threshold here, you will not see the recoil, but you can see the Bremsstrahlung photon or the Migdal electron. And then you can easily see from these two comparisons, if you do now, if you assume the Migdal effect and probe your parameter space, the limit is accordingly stronger than the Bremsstrahlung. And so that's why people typically don't even bother about doing the Bremsstrahlung, because Migdal is giving you the same mass reach, but a stronger probe of the whole thing. And then just putting it on the full picture. So this time now, so this is the light mediator here with a heavy mediator, but this is what is putting experiments like xenon-based xenon TPCs on the same footing as super CDMS or CMS Lite. Is just a version of super CDMS and CREST. So this is why they can actually push to those lower masses, even though they are not, as an experiment, they are not a low threshold experiment, not compared to what we've shown you yesterday. Now, normally what I would say at this point is, so the Migdal effect has been observed by beta and alpha radiation, so induced by charged particles. It has not yet been observed induced by a neutral particle, so like a neutron. And so this channel is highly speculative still and needs to be calibrated in a way. I mean, we need to understand what the response is really. However, and this is pretty new, at Taup 2025, so end of August. I was not at Taup, so I don't know any detail. I just got this picture from one of my postdocs. You can see preliminary Migdal effect candidate, the neutron. So basically, this is a DD generator based experiment. So the neutrons are being generated with a known energy, sent into a gas detector, and in the gas detector you can actually nicely identify the tracks, so you can detect the topology. And what you want to see is basically a topology that has both a neutron recoil and an electron, so both coming from the same vertex. And yeah, it's not nice to be seen here because they're the heads in a way, but apparently there is a Migdal candidate, and I tried to find the slides online, and on the slides that I found online, this slide is not part of it. So apparently the one that was uploaded is not the same as this one, and I didn't find yet whether anything is published. So I could imagine that over the next couple of weeks or months, something could appear on arXiv. If this is true, this is actually really fantastic, because this would take the Migdal effect a little bit off the highly speculative part and provide more access and really more means for experiments to probe also the lower ranges. So yeah, that's just let's wait and see, but it's looking actually exciting in a way. Yes.
Charged particles, right? But charged particle, how do you kind of separate the NR from the R? Won't you just
So I don't know how the measurements were done. They're actually pretty old, but in the end, I mean, if you have the topology, then so when I would, I guess that you would need something that can resolve really the kinematics. And if you have, then you have basically something incoming and something scattering off. But I must admit, I don't know how the experiments were done back then. Yeah. So now the other part is dark matter electron scattering. So one argument is also, so now we have built our detectors already. We are stuck with xenon, we are stuck with silicon, germanium, calcium tungstate, etc. So what if, we just go away from trying to search for the dark matter nuclear scattering, but rather look into dark matter electron scattering, because the electron is a much lighter scattering partner, right? And so what you have here, again, the mass region, here's the maximum recoil energy that you can get. And if your dark matter particle gets much lighter, again, then the mass of the nucleus, the energy transfer or the momentum transfer is getting really bad. It's really getting poor. And you see, again, maximum recoil energy here, the different elements that you can that we are using. And just so the calcium and the oxygen, for example, that's in CREST, you have a compound of calcium, oxygen, and tungsten, and then you would, of course, the dark matter particle would scatter on either the calcium or the oxygen or the tungsten. So you need to look at them individually. But what is true for all of them, if you go somewhere, and the GeV range is roughly the proton or neutron mass. And so if you go below that mass range, you see anyway, so already at 10 GeV, the maximum recoil energy really significantly drops. The electron recoil energy at the same dark matter mass, if it's scattering off the electron, the lower you get, the higher, in comparison, the higher the transmitted energy is. And here we are talking about order to orders of magnitude. The one thing I should, of course, point out that the electron recoils are largely inelastic. So it's not the simple picture that we have with dark matter nuclear scattering, but instead the energy transfer depends on the orbital of the electron, and it depends really on the motion of the electron. And again, we need to keep in mind this is not a free electron, and the electron is what in the end determines the typical momentum transfer. And just to give you a picture on what it means in terms of what we can observe with our detectors. So obviously, again, the picture that you should have in mind is that we have dark matter particle coming in, and it releases an electron. If it doesn't kick out the electron of its bound state, then we can't pick it up. But it needs to be released from the atom. And so in the end, what the dark matter, so chi for dark matter, needs to provide is an energy that is larger than the binding energy. And if you turn this argument around, so if you solve for the dark matter mass, assume the dark matter velocity in our halo, then you get a bound a lower bound on the dark matter mass that you can probe, depending on the binding energy of your atom or your material that you're using. And typical binding energies are somewhere in the range of 1 eV to 100 eV. So it's in the eV range, and just if you take the 1 eV, so this suggests that 300 kV in principle is accessible. Or in other words, we can really go well below the GeV scale of probing dark matter if we are able to measure the released electrons. So this is just the key idea here. And of course, this tells you that when you want to pick a good material, the smaller the binding energy, the smaller the reach that you can have. And so there also xenon is not ideal, or noble gases in general are not ideal. So the electrons in a noble gas are actually happy where they are. They have a high binding energy. And so you are well above 10 eV typically. And whereas in, for example, silicon or semiconductors in general, we are more at like the EV scale. And then the next question could be, okay, are there actually materials that have even lower binding energies? So if you're looking for dark matter electron scattering and want to build an experiment, you're looking for materials with a small binding energy. Now, similar to the dark matter nuclear scattering, here's also a mass formula for the dark matter electron scattering. And again, this is what we are trying to measure, the expected interaction rate. This is the theory that we want to probe, so the cross-section of this interaction and the dark matter mass. The halo properties we have to take into account as well. So the same story as with dark matter nuclear scattering, depending on the velocity distribution that you have and the density that you have, your rate scales with that. But now we also, and actually that was also the case for the dark matter nuclear scattering, I told you we need to take into account that the nucleus is an extended thing. It's not point-like, so we have to take the nuclear form factor into account. Here, we need to go one step further. It's not just like the form factor, but really the entire properties of your electron system, of your material. And again, here is also a term, is again the dark matter form factor. And it's the same story as before. We are in the situation where we have to distinguish between a point-like interaction with a heavy mediator or an interaction with an ultralight mediator or anything in between. And this is, again, this is folded into this part. Now, this is what we want to observe. So again, Bremsstrahlung, it's a photon. Migdal effect, it's an electron. Dark matter electron scattering, it's an electron. So what we want to dive into is semiconductor charge detectors, because these are the detectors that are sensitive or pushing towards the low mass region by observing the charges. And I also mentioned yesterday already, when you're doing physics, so both actually theory and experiment, but you're talking from the experimental perspective, the moment you want to make the most out of your detectors and really get the most sensitivity, that's the moment when you need to start off not only thinking about particle physics, but you have to widen your knowledge and actually go back, in our case, to condensed matter physics. because I said already multiple times the electron is in a bound state. And then, so in condensed matter theory, you're not in this particle picture, but you are in this band structure picture. So here you have momentum space, here you have energy space, and you have certain, so you have these two regions. You have the valence band regime and the conduction band. So as long as the electron is in the valence band, it's bound. The moment it's moved into the conduction band, it is free to move across your semiconductors, so silicon in this case. However, it's still constrained to certain points in the momentum energy range. And so these are the allowed levels. And now, in order to, first of all, get a certain the probability for it, for the electron to be freed, it depends on the amount of energy. And then, first of all, if you, for example, see, if you want to go from here to here, so this in terms of the energy, this step from left to right requires the least energy to happen. The gap is the smallest. However, we are in two different points in momentum space, so we need to get extra momentum in order to obey momentum conservation. So this is doable, but less likely than a direct transition here. However, from here to here, you need more energy. So it really depends. The probability is not just the more energy you have, the more the more likely you are to get an electron out. So it really depends, again, on how much energy you get in the end. And so this is also telling you that really calculating the expected differential rates. This is not particle physics, this is condensed matter physics. And either you're able to do it yourself, or like me, I'm not. I'm happy that someone else is doing it, and you can find really nice tools from experts that are doing it. And QEdark is one example, QCdark, and others. There's tools that are being used, that we are using, that are actually giving us the prediction of the differential rate. And this is how, in the end, for example, for a 500 MeV dark matter particle scattering of electrons in silicon for a point-like interaction, this is the differential rate that you're getting. So it's rate over deposited energy. And the things that you can observe is, first of all, most of the signal is at the EV scale. So we need to have silicon, if you're using silicon detectors that have to be sensitive to the EV scale. You have a sharp cutoff at the band gap because, of course, going back to this picture, if you don't have enough energy to lift the electron from the valence band to the conduction band, you just don't have an electron. So you can't go below the band gap. And then the other thing that you're seeing here, all this ups and downs and so on, this is not statistics. So it's not just a simulation with too few statistics, but this is really the band structure. So like I said, it depends really where you are here on the band and here on the band, and whether you're going straight, so same momentum, or whether you need extra momentum. This defines how likely this energy results in a transfer. So this is why you have all these features. This is really the electronic structure that you're seeing behind it. Yes, please. So why is so yeah, actually that's why do we end in general? So the answer is it's a good question. Why are we all around the EV scale? Why is it not getting higher and higher in this direction? And then also the so actually this is a little bit misleading, I should say. So this is not the deposited energy, this is the energy of the electron, and the energy is really, it's driven by the electronic system. So really the momentum, the typical momentum transfer is of the scale alpha, so fine structure constant times the mass of the electron. This is around 4 keV, and now if you transfer this into transferred energy, this is in the 4 eV range. So it's really you're not, you need to get out of the picture that you have something coming in and then a recoil, and the higher the incoming energy, the higher the outgoing. That's not the situation anymore. You have the electron, and you share the energy, and this is defining whether the electron goes out or not. But it is not not entirely defining with how much energy it. I mean, it does contribute to it, but really the amount of energy that the outgoing electron has is different, because some of the energy it's getting just from the shell where it is sitting, and the momentum it is already having, and the incoming energy mostly determines the probability for this to happen, so that it's being kicked out or not. So just for example, when you have a very high incoming, so say you have an electron sitting here, you have a lot of energy coming in, and this electron is lifted all the way up here. Then first of all, this energy is lost. So it's not available as additional kinetic energy. It's first of all just to get to this other state. And now the kinetic energy, whatever a little excess is there, this is when you start to get actually in the regime, when you're close and closer with the states, the extra kinetic energy. This is what we are trying to observe. But you always have to first subtract the energy it got in order to get to the next level. So that's the key difference. And this is why, in the end, even with higher dark matter masses, so the recoil energy gets a little bit higher, but it's really always sitting around this EV scale, because again, it's just driven by the electronic system, how much kinetic energy you're getting in the end. So that begs again the question: how do we measure the EV scale spectrum here? And this is where what I mentioned at the beginning of this lecture, that there is still a little bit about the phonon-like detectors, because they can, in the end, they can measure charges. And I said yesterday already, so the semiconductors, they generate phonons and they generate charges. And we just discuss a little bit, what about the charges that you can basically directly collect them yourself. So here was the example: you have a plus minus, you have a drift field, you are drifting the electrons across the detector, and you just collect them with an electrode. But you can also use them to actually amplify the phonon signal. And this is what is normally a little bit confusing. And actually, it also begs the question: if you use the charges to create a stronger phonon signal, but you're interested in the charges, so is it now a charge detector or a phonon detector? So the sensors are clearly phonon sensors, but the entire detector wants to measure the charges. So this is why this is still here a little bit in the part of today, the charge observation. And again, the reminder: you have a particle coming in, you have electron hole pairs being generated, and you have phonons. Now, yesterday we talked about how the phonons are being collected. And I just reminded you of when you have a drift field, you're drifting the charges and you can collect them with electrodes. But if you're doing one trick, so if you're applying here a very, very high charge, or high electric field, what is happening is, so you have normally, say we are in vacuum, you have an electron hole pair, you have your capacitance, and you just accelerate them in vacuum. They get the final velocity depending on the voltage that you apply. Now, we are not in vacuum, clearly. We are in a silicon crystal, we are in a germanium crystal, any kind of semiconductor crystal. And what is happening when you apply a really strong field is that the electron hole pairs, they are starting to accelerate, but before they get to their terminal velocity, they are seeing other atoms, other nuclei ions. So they are basically not able to just accelerate freely, but they are in the system and this entire lattice, and they basically scatter around is wrong. It's too exaggerated, but basically they interact with the surrounding atoms and they transfer their energy into lattice vibrations rather than accelerating to their final velocity. So in the end, what is happening is that the electron hole pairs that are being accelerated dissipate their energy in further phonons, because again, they are not accelerating to the full velocity, but instead they are hindered by the surrounding atoms, and they share their excess energy with the lattice in terms of lattice vibrations. And this is what you can see here, called secondary phonons, because you have the ones that are happening promptly on their own, and then those that are coming from the electron hole pairs that are being accelerated. And the amount of secondary phonons depends on the size of your voltage. And this is what is basically showing here. You have the deposited energy, and then you have a certain amount. So N is the number of electron hole pairs that has been generated. This is the charges, and this is the applied bias. So this is also, yeah, in energy units, EV. And basically, so first of all, the more initial electron hole pairs you have, the more phonons you get. But also the higher the voltage, the more energy you're putting into the amplification, really. And so in the end, the total energy that you get is the prompt phonons. In the end, the recombination energy of your electrons and holes, but also this extra term, which we call Nikanov-Trofimov-Luke amplification, according to these three physicists, or short NTL. So what you do, just to recap, is that you can, you are in this case trying to observe the electrons or electron charge, electron hole pairs, and you are amplifying the tiny charge signal with a large bias voltage into a phonon signal. And just to say, when we are saying a high voltage, we are still talking about 100, 150 volts. So it's not like PMT 1000 volts, 2000. This is still 100 volts range. But for these kinds of detectors, this is a high voltage. So normally they are just operated at 2 or 3 volts. And so this is really a cryogenic calorimeter without charge readout, in order to be very sensitive to charges. So that's the funny trick here. And the experiments that are using or have been are using this nowadays the most. So Edelweiss has been using this as well, but Edelweiss is disseminated, is super CDMS. And yeah, I showed you these pictures yesterday already. So this is the one here with charge readout. This was this picture with the sensors where you have both phonon and electrodes. And here, this is also a picture that I showed you where you have many of these tiny QETs on top and no electrodes, because in the end with these, and we call them high voltage detectors, we want to measure the charges, but in terms of a phonon signal. And then the question is, okay, how far can you push this idea? And so this is getting me to the HVEV R&D program of SuperCMS. So HV stands for high voltage, and EV for the EV scale resolution that is being achieved. And yeah, before getting into this, what is great with this kind of observing charges is you have a very high time and energy resolution, but you have very poor spatial resolution. So the part of the spatial resolution with the ISIP detectors also comes from the electric field, and also from the phonon signals, but a lot also from the electric field. So they are not really great in spatial resolution, but again, the timing resolution is tenths of nanosecond. So it really just depends in the end on your sampling rate of your digitizer. Now, yeah, what I want to show you is going here. So these, again, they are, yes? Mm-hmm. So you mean the signal, how it basically looks the same. So with these detectors, we cannot resolve. So it would be interesting. It would be great if you could resolve the prompt phonons and the secondary phonons. We cannot yet. So there's attempts, to get there, but to first order, the pulse shape looks the same. Because in the end, the secondary phonons is totally dominating the signal. So you have a tiny prompt phonon signal and a dominating secondary signal, and that then has basically a similar characteristic. Yeah, but thank you. Okay, so the trick here, so these are about a kilogram, 1 to 3 kilogram scale, depending on whether you have silicon or germanium. But sometimes when you want to really push resolution, it's always easier to start with a small device because smaller devices have less position dependence, have typically a higher collection efficiency and so on. So you start with something small. And so Super CMS was trying to see how far the whole idea can be pushed with a small device. It's about 1 centimeter by 1 centimeter and 4 millimeter thick. So it's a gram scale detector. But the idea is still the same. So on this chip here, you have the QETs, and then, yeah, like I said, you operate here with about 100 volt. And now in the very first iteration, so this is now, I think this is from 2017, I think, the 17 or 18 is plot. So this is actually an old plot, but I really like it because, first of all, what is shown here, so it's operated at 150 volt, and what has been used to get to this plot is a laser. So you have a laser with an energy or wavelength that is just high enough to be above the band gap, and this means your incoming photon has just enough energy to release 1 electron. The energy is not enough to release 2 electrons. So you know, whenever you have a photon coming in, it either releases 1 electron or no electron. Now and then yeah, for the laser, since you're sending a laser, you have also a trigger that you can use. You know exactly when you're sending the photon and when to expect a signal, so you can trigger on this. And this is, first of all, yeah, like I said, it can also be that the photon doesn't generate any electrons. So this is why when when this was triggered, every so often you have 0 observed energy, because again you're triggering not on. Yes. That's just, yeah, basically the baseline resolution in the end. So yes, the baseline resolution goes negative, but just because these are really noise fluctuations fluctuating around the baseline. But yeah, particle deposition wouldn't go negative, yeah. But this is, yeah, again, this is 0 energy deposition plus minus the baseline resolution. But every so often you're observing 1, 2, 3, 4 electron hole pairs. And it just said a single photon cannot get you more than 1 electron. However, when you're not using a stabilized laser, then it's a Brownian process per laser event, basically how many photons you're sending. So you can send 1 photon or a Brownian around a certain lambda. So lambda is, yeah, your mean. Mean is the wrong term for Brownian, but mean-ish. For a Brownian. And so basically you're saying, okay, most of the time I want to send 1 photon, but Brownian statistics gives you sometimes 2 photons, sometimes 3, sometimes 4, etc. And so when you just, the green one is just Brownian statistics for a lambda of 1, and you see the data really nicely aligns with that Brownian statistics. So it's telling you a couple of things. So first of all, with this device, you can really say that it was 1, 2, 3, or 4 electron hole pairs. So a really sensitive, first of all, to a single electron hole pair. And so the threshold is low enough to really observe a single electron hole pair, and the resolution is high enough to distinguish between 1, 2, 3, etc. So really, with these devices, you are in a quantized regime. You have an ionization detector that is having such a high resolution that you can distinguish between individual charges. And so this is for SuperCMS. It was back then the very first time, and anyway, for these types of detectors, that quantization has been observed. Yes.
Is the energy released like 100 of EV because you have this bias voltage, but then does this make this in a metastable state? Because you only deposited 1 EV, but you got 400 EV, so it seems like you should also be able to just tunnel, right? Because it's more energetically worth to do this.
Yes. Yes, so actually there are 2 points. It's very good. I didn't really mention. So this is the electron pairs, and yeah, Ita is completely right. So first of all, what we are observing again is the phonon energy, and that depends on the voltage you are applying. So for 150 volts at 1 electron pair, you're basically getting, so 200 is here, and this is 150, this is 300, so 2 electron pairs are basically 2 electron pairs are 300 eV, so this is just the amplification. Now the question is, if you have this high voltage, do you every so often just get an electron without any energy deposition? So it's sitting there, sitting in their potentials in the crystal, but you are really drawing on them. And so if you're, for example, if you're going too high in voltage, then you start to see actually a current. And so that's something, first of all, that that you do initially. So when you have your silicon, you want to pull out the electrons that are sitting in a shallower potential, because so you don't want to have them mess with your signal. So normally you first apply a higher voltage to draw those electrons out of their shallow states, and then you go back to the lower voltage, so then you reduce some of the that leakage. However, it could still be that, and we call this impact ionization, that the electrons that you're accelerating, they're not just generating phonons, but on their way, they could kick another electron that's still sitting maybe at a little bit shallower, deeper, but still to shallow state. They could kick them out. And then so on along your way, you're getting, let's say, halfway through another electron that is then contributing. And so this is then something, the resolution here was not yet, or this is not in log scale. When you go to log scale, you would actually see that in between, and later on I think I have a plot that shows it, you will actually have in between fill-ins that come from this impact ionization, because you get a partial amplification. So yeah, these things happen and they need to be taken into account. So then with the latest run of next to latest run at SuperCMS H3, the latest published run, it was operated at Nexus. So Nexus is an underground facility at Chicago Northwestern. It's not very deep, but deep enough. And I also mentioned yesterday that with these tiny devices, you don't have to go super deep. And in this case, they were operating 4 of these modules, so 1, 2, 3, 4, and then you can play around a little bit with how you organized your QETs. So here, you always, you basically have a different mask. The QETs have a different geometry, so you really can play around and test what is best. But this is just for completeness, saying where this is standing right now. And there's currently a run, or there has been a run at SnowLab also, that is currently being analyzed. But basically, what you can do with these multiple devices, also you can do a coincidence measurement. So you can reduce your background by saying, okay, if it was dark matter would not be in coincident with these two or with any two detectors, would scatter worms or not at all. But for example, if you have here, a source that is, for example, something coming here through and then triggering both detectors, or when you have light leaking in that would trigger both detectors, you can use the coincidence to reduce the background. So, but yeah, now I want to transition to what are really charge detectors. So again, here with the phonon detectors, I was cheating a little bit, because in the end they are sensing the phonons, but they want to observe ionization. Now, when you really want to go towards charge detectors, CCD-based detectors are actually state of the art in what you can really achieve. And I should also mention, they are, you will see in the results, they are stronger than, for example, SuperCMS H3 EV, because they are really, also in terms of resolution and so on, they are brilliant. And just to give you an idea how they look like in terms of size. So first of all, you can see you have here one sensei module with a strip with many with a CCD strip. Here you have a DOMIC module And just to get an idea of the size, and yeah, you normally then you stack multiple modules and read them out. So you really have a layer of multiple CCDs, and yes, CCD really principal idea like in your CCD camera. But again, yeah, first of all, here just to give you an idea of the size, it's a different size, and also a key difference is that in terms of, let's say, standard CCDs, they are rather thick. So they are, yeah, in this case, is an old DAMIC picture, but from what I saw, also the latest version of their CCDs are similar thickness or same thickness. And the key idea here is, first of all, CCD is pixelated, so you have many pixel. They're silicon based, you have a voltage applied, and now if you have here, for example, a interaction happening, releasing an electron, then the electron hole pairs, they are being drifted, so that's the same thing as what I just told you. But here in this case, it's really the electron hole pairs, they're drifted until they reach the area of the pixel area here. And depending on where the interaction is happening, so say you are here under this pixel somewhere in the middle, you have a certain diffusion happening. So you have a broadening going here, so that you have scatters, and the scatters broaden your signal. And so depending on how deep you are, the more stretched over pixels your signal is. So just now looking from the top, when you were like super close below this pixel, only this pixel would carry energy or collect electrons. But the further you are down, and you are here actually having an avalanche process, the further you are down, the wider your hit pattern is. And so from this, you can get a measurement of the Z direction. And then, of course, given the pixels, you also have a XY resolution. So in contrast, to the devices I showed you before, where I said they have excellent timing resolution, these devices have excellent spatial resolution. You can really, on pixel level, tell where the event was happening. However, they have no timing resolution, because you're taking a photo of over a long, you have a long illumination time, basically a long wait time until you have collected so and so many events, but you don't know when the events happened. Oops, sorry. And so then this is also an old picture, but just to give you an idea. So yeah, you not only get position dependence, but also the topology. So given, so say you not only have like one hit, but you have something like a muon that is propagating, then you would get actually not a single circular shaped kind of thing, but you get an entire track. Or when you have something that is highly ionizing, you get a thicker blob. And if you make this picture a little bit prettier, then you get also an energy scale. So again, here alpha, muon, electron is scattering more. So this is basically the picture you get after a lot of analysis. And I think you have won student projects on sensei data. So I guess you know, I don't know whether you did the project already or whether it's coming up.
They're on it, but also
Okay.
the data is simulated, and the decision was that if I try to make actually something that looks like electrons, it's not.
Okay. So yeah, so if you had electrons, they would be looking more like this. And yeah, this is also to say, to get to such a point, I mean, there are many analysis steps. So for none of the, also yesterday, no, today, I'm not showing you all the cuts and classifications that you need to do in order to get to a clean picture in the end. I mean, there's always a huge amount of effort in it until you find something nice like this. Now, this is just the classical CCD, but then going but yeah, first of all, how do you actually read out? So that's something that I quickly wanted to tell you. So in the end, yeah, say you have here your You have a 3x3 pixel CCD, and the key idea is just when you have your charges, so you have your electrons that are being drifted, they are now sitting in your pixel, you need to get them somewhere to the readout stage. And with charges, the easy thing that you can do is just dealing with potential. So if your charge is sitting on a potential and you lower a potential, it will drop down in that potential. So basically, you move by here you have the potential, basically the state of your pixel, and here the well accordingly. And then when you see here, when you lower it, you can the electrons can populate both areas here. Then if you raise this part again, the electrons will be constrained to this part, and so this way you can just move them along until the readout stage. Now that is fine, that is nice, but what is a really cool part about these devices, if you go one step further and not just measure the charges once, but multiple times. And this is where Sensei comes in, because they were the first to use what is called skipper CCD. So the idea is here, you have your charges, say they're sitting here, and when you move up this this potential here, then the charges will go to the lower potential next to it and drop down here. You can measure. Then if you now lower this potential, they fall down here, and now you can do the same game again. So you skip them around, and so you move them from one gate to the other, measure them, move them back, measure them again. And the idea is, if this is really uncorrelated measurements of those charges, when you measure them over and over again, you should gain a factor of square root of n. So again, same charges, you didn't change them, but your measurement is intrinsically with a certain uncertainty. And so if you measure n times, you should get an improvement of 1 over square root of n. And this is what you're seeing here. So the readout noise over the samples per pixel. Of course, the more often you do it, the more time you take. So this is why also you see here the readout time in milliseconds per pixel. And this line is the prediction. If it is only Gaussian uncorrelated noise, then you should go down this line, and you see that this is actually following this trend very nicely. And then you need to decide at some point, okay, how long am I willing to wait? So how long do I really measure? And this is not, I'm not talking about minutes or so, but hours. And I think I don't know how long you in the end pushed it, but
multiple images, like I think hours most, because they accumulate the high energy stuff that you showed earlier.
Yeah. Yeah. So that's hey. Just to give you an idea of the time scales that we are talking about here. And then again, that's also why I said there's no time resolution of these devices. But also for the skipper CCD, so like I showed you for supersymmetric H3EV, you get sensitivity to single charges with a high resolution. And now this is just, for example, one picture. This is one charge, 2, 3, 4. You see here single charges can be seen, and more prominently on this plot. So reading out every pixel, you see that you can really distinguish between 1 charge, 2 charges, 3, 4. So the same is true as I said before. Not only do these devices have the threshold for being able to see a single electron hole, a single charge, but also do they have the resolution to distinguish between 1, 2, 3, etc. And I'm showing you also an old plot here from 2017, but this is one plot that I really like because it's showing here that this is not only like maintaining this high resolution at the low charges, but also here we are at nearly 800 electrons, and the number that I found on the Sensei webpage was saying that basically even above 1,000, about 1,000 electrons, you still can resolve them. So this is not only like very good at the lower energies, but you still get a good resolution also at the many charge. pixels. And now that is Sensei, and then of course Dharmic is not stupid. They understand that skipper CCDs are great, and so Dharmic M is also transitioning to skipper CCDs. And actually, I'm just seeing this says Dharmic M prototype, because before I had a prototype picture. This is not the prototype anymore. This is the actual Dharmic M module. And you're seeing again here, you have on one module, you have 4 strips. Each strip has 6,000 by 1,500 pixels. Then you have your 4 strips per module, and in total 26 modules. So we are talking more than 1 million pixels here. And yeah, each module is about 3 gram. So we are still, below the kilogram scale, or around. No, that's wrong. I think. No, it's 26 modules, right? So it's below the kilogram scale, but approaching there. So that is, again, one of the Dharmic modules. And here, similar picture as before. You have pixels, and now instead of having the scale as a color bar here, you just have directly the entry of the amount of charges that have been observed. And just to give you the same picture as before, you can see here, same point. Also, Dharmic M manages to see individual charges and separate them from 2 charges, etc. And so in this case, Sensei was at about 0.067 or so charge resolution, and here it's about the same scale. So in both cases, 0.07. So they are performing similarly well. And just to tell you also where they are located. So Dharmic is at the underground lab in Modern, and Sensei is right now at Snow Lab. But the other point that I want to highlight here is that all 3 devices that I showed you, the picture in the end looks very similar. So no matter whether you measure directly the charges, or whether you amplify them first and measure the phonons, in all 3 cases, the signal is quantized. And this means that this picture that I showed you before, the slide that we have discussed already, here this is not yet quantized. So we cannot just compare these data with this model and say we found or we didn't find dark matter, because we first also have to turn this into a quantized signal. So basically what we want to have, we have this, and what we want to have is a prediction in the quantized regime. And here it's just saying ionization model. I can tell you it's not, it's also not the most complicated thing, but it's not like there's this one ionization model that just does it for you. There's a certain statistics behind. There's also Fano statistics. The Fano factor has to be known and understood. And so overall, this translation also backs some systematic uncertainty. So just to keep this in mind. And when you do this, and this is where I mentioned there's also a log plot for at least a SuperCMS H2EV device. When you do that, then you can, in the end, you have your data. So this is now not laser data anymore. This is really background data where, so basically a search for dark matter. And then when you compare this with your dark matter model, you're basically comparing, and you can see here, okay, this dark matter model has been excluded, not because of the first electron hole per peak, but because it at this cross-section that is drawn here, it would be higher than those peaks. And then coming back to the question we had earlier, I told you already that you will find fill-ins between the peaks, and this is for the impact ionization that I mentioned already. So you have the electron being released and being propagated and kicking out another electron that is now also being amplified, but partway through, so it's only getting a partial amplification. So a 1 electron hole pair can in the end look like something like 1.5 electron hole pairs. The other way around is also true. So you could have an electron propagating, and there's actually an empty state where it could fall into. So this is what we call charge trapping. It could be trapped in a potential and not make it all the way to the readout part. So it will not be accelerated further. It will not generate more phonons. So a 2 electron hole pair event could also look like a 1.5 electron hole pair event. So these are all these detector effects that you have to take into account, measure and model. And then coming to the state of the art where we are right now. So this is the latest plot that I could find from DAMIC M 2025. A lot is going on. So let me first, remind you of the two form factors. So this is why you always see these two plots, like discussed before. And then depending on what type of model you have, you also have different generation mechanisms. So in this case, it's a standard freeze-out scenario. Here you have a freeze-in scenario. But again, this is not about dark matter production, but really about measuring. But basically what in the experiments, what we want ideally to do is meet theory. And theory gives you, with these mechanisms, a target line saying, okay, if the dark matter was produced via freeze out or via freeze in, then at this mass we would expect this cross section. And this is why this is really also a nice area to reach. But I can tell you already, should we surpass all of this target and don't find dark matter, there are different models that will follow. So there's basically, we call this relic targets. The relic target just depends on the details of the production of the model. And this is not to say once we have probed this target, it's over. It's just saying that then this production mechanism is maybe not the right one. And now you're seeing here DAMIC M, the latest results. They are actually probing into this interesting region, or crossing the freeze. And it's not a region; it's really a line. And then followed by Sensei, and you can see Sensei is pushing it a little bit to lower masses, and then Super CMS HVEV is this line, I think, and the latest results. A little bit further down, and I don't know, so I'm not on Super CMS anymore. I know that a new publication is coming up, but I don't know where this will be sitting in this parameter space. But the key point is really that the Skipper CCD devices, they are really the one leading the field in these searches. Yes. Okay. So I didn't find, I was looking for the latest sensing results.
So it's not so DAMIC, the previous result right before this one was data modulation. Sensei put out their data modulation, that Sensei data modulation is better than DAMIC data modulation, but the regular analysis is not.
Okay.
I think it's what we have.
Okay. Good. And the other part I want to point out, so now we are in the world of the MEV axis. So before, all the plots I've shown you was always GV oriented. So in order to span up to the TV scale, going down to the MEV scale, but normally the axis label is GV. Now we are really at the low masses where the axis label transferred to MEV. So I think, the dark matter is. Yeah. What Laura is referring to, so basically DAMIC has a very comprehensive background model for their analysis. And in one of their analysis, not in this one, I think it was the one before, they had an excess over their background model that they couldn't find any background explanation for. It really depends on who of DAMIC you ask. So when you ask Dan Baxter, he is telling you, no, this is not a dark matter. It really depends a little bit. So I think, or let me phrase it differently. There are on the list of what it could be, there are also still 10 other things. So it's not excluded that some of it, there is also dark matter inside, but there are just so many other things. The homework is not complete to come to this conclusion yet. Yeah. Yeah.
I think this result actually, I would guess it probably is that.
I think so too. Yeah.
I don't.
Yeah.
I think very careful about how they presented their access, because I think, as you said, some of the collaborations have disagreements about how much you actually think of it as an access.
Yeah.
So again, in the title they had it, but then I don't remember exactly how they presented it. But it's not.
Yeah. Okay, so I think I have, yeah, we started a little bit late, so I think I have until 5 past, so until 35. So I want to, yeah, bring you back to the big picture, because so far we talked a lot about those thermal dark matter candidates. So this is basically this picture. We have the standard model, and we have this extra particle. And I already mentioned that maybe one particle is not enough, so maybe we actually have dark bosons, some of which could act, or they could act as the mediator. So a dark photon could be. So first of all, we not only have like the vanilla WIMP, we also have light dark matter candidates, which is still kind of a WIMP model, just a little bit extended. And then again, we have dark bosons, which could actually help with the connection to the standard model if the bosons that we have are not sufficient. Now, the thing is that so far, yeah, I've only talked about those as a potential mediator. However, they are actually also suitable candidates for dark matter themselves. So in principle, there's nothing against dark photon or axion-like particle to be the dark matter that we are looking for in the dark matter halo. And this is now where I'm coming to this part. So this is what I've discussed so far. But now we're getting into the region where we are asking ourselves, is the dark photon or the axion, the ALP, actually the dark matter? And so this is where I want to go now and discuss a little bit how, with our experiments, we would observe bosonic dark matter interactions. And this is coming back to this picture. So we have, yeah, now dark matter absorption. So it's really like thinking of a boson, of a standard model photon. A standard model photon could be absorbed. It could do Compton scattering. And I should actually also put Compton scattering here in quotes, because Compton scattering is defined on free electrons. So we are looking here still at a bound state. And so this is only approximately the Compton scattering if you're actually freeing the electron from its bound state. But yeah, just to be very precise here. But still, it works well if you take a lot of the Compton scattering standard model process and translate this into bosonic absorption, bosonic observation. And in general, within the direct dark matter particle experiments, the interactions or the processes that are being considered are the dark absorption, where you basically have an incoming boson. So the A is the axion-like particle, A prime, capital A prime is the dark photon. So you have an incoming dark boson and outgoing electron. Then the other one had dark Compton scattering, similar picture. You have an incoming dark boson, but you are now actually translating the dark boson into a standard model boson, and you have this outgoing photon, or you can have, and this is just happening for axion or axion-like particles, an interaction with two photons. So you have a photon here coming actually from the nucleus itself, or it should rather actually say from the magnetic field, but then the matter where this is happening, and you have an outgoing photon. And the coupling constants are shown here. So the coupling of the ALP to the electrons is GaEE. Epsilon is the kinetic mixing between a photon and the dark photon, and this is the coupling to gammas. And I will not talk about this one. So this is basically what you could call dark Bragg scattering. And there's someone who has analyzed data already in this regard for super. So you just mentioned you did the super CDMA or the CDMS. Yes. So there are results out there for this kind of search, but these is basically for solar axion or solar ALP searches. So it's not the subject of today. It's a cool signal actually to search for, because it comes with a Bragg pattern that is very different from everything else. So in terms of signal to background, it's actually a really cool thing to do. But still, I will actually focus on these two, and I will start with dark absorption. So it really, if you think back of photoelectric effect, that's what it is really based off. You have an incoming photon, you have an outgoing electron that carries the energy of the incoming photon, keeping in mind the work function W to get the electron out of the system. So that's yeah, the normal photoelectric effect. And now the only thing that you're doing is that you're replacing here the incoming photon with a dark boson. And then what you have in cold dark matter, because if you're making the assumption that the dark boson is making our halo dark matter, it should be cold dark matter. So this also means that most of the energy is really dominated by the mass energy. So in other words, what we are observing here is the energy of the incoming particle. In this case, it's the mass energy. And so, in other words, what we are measuring, when we are measuring the electrons, we have a direct handle on the incoming mass of the dark boson. And this is what is shown here on this plot. So you have deposited energy. If you have a perfect detector, and this is also true for the photoelectric effect, you would get an exact line that is at the position of the incoming photon. So this would be if you have a 15 keV photon causing photoelectric effect, you would observe an electron with an energy of 15 keV. If this is not a photon but a dark boson, it's not yeah, it is in the end the mass energy, like I said. So this is basically to say if you have a 15 keV peak in your spectrum, then it would refer to a 15 keV signal, 15 keV mass dark boson. And the widening, of course, just comes from detector resolution. And the rate itself scales with the coupling squared. So this is a little bit the annoying part, yeah, that it scales with the coupling squared, but that's all right. So, and then the other key part is here that you have, like I said, it is really directly related to the photoelectric cross-section. So the thing is, with detectors that, yeah, like Super CMS and others, those solid state detectors, this is basic to say you're searching for a peak in a peaky spectrum. So this is for germanium. In germanium, you have these huge peaks, and these huge peaks are nice and annoying. So they are intrinsic to germanium. So in the end, what you can do is you can use a neutron source. There's a lot of germanium 70 in your germanium crystal. You can use a neutron to activate it to germanium 71. Germanium 71 will decay via electron capture, and depending on from which shell the electron is being captured, a different amount of energy is being released. So from the K shell, it's 10 keV, L shell 1 keV, M shell 100 eV. And so this is then where you expect your peaks to land, depending on the branching ratio. The K shell capture peak is really high and strong. And since you know exactly in a germanium spectrum where to expect, you have a really nice calibration. So yesterday there was also a question, how do you calibrate your devices? So for germanium, this is one way to calibrate. You use a neutron source to activate and measure those capture peaks. So great for calibration, and over the time they also decay away a little bit. However, this is really annoying when you're looking for a dark boson signal. And so in the end, what you do when you do an analysis, statistical analysis, you're not directly putting a limit on, in this case, on the dark boson, but you're really actually setting just an upper limit on the rate. So this is really just when you do standard Poisson statistics, just a counting experiment, and you see per energy region, you're asking within statistical fluctuations, how large could a signal be that is hidden in this energy range. And then, so this is really, yeah, just a upper limit on your count rate. And you can see that, yeah, of course, where you have, here's the energies, where you have those peaks, so this one is not there, of course, so just the blue peaks, your sensitivity is way worse. So the limit on the rate is really terrible where you have the peaks, and it's getting better and better where you have no peaks. And now then only the next step is where you actually put in your theory and interpret that rate. And you could interpret the rate either with an axion-like particle doing the process or with a dark photon. And so this is also, to tell you that normally this is really just an in the end interpretation and phenomenology. This part, this is for sure. This is just what the data gives you. But how you interpret what you see, here you can just plug in the different models. And here you see now the mass ranges of the axion-like particle. And sometimes you see the dark photon not as A prime, but as V, because it's a vector boson. And you see the sensitivity goes all the way down. So this is KeV, this is 100 eV, this is sub 100 eV scale. And this is really because where the threshold is. So I said before, basically the lowest energy you can measure is directly translated into the mass that you have. And with these super sensitive devices, so this is now supersedium as HV EV, the band gap of silicon, this is now silicon, is at around 1 electron volt. And so this is basically to say that if you have a dark boson that is coming in that has a mass of, let's say, 2 electron volt, it would be massive enough to get a electron from the valence band to the conduction band, and you can actually see it. And this is why in the end you actually go down all the way to, this is where the band gap is in the end, so to the EV scale for dark photons and axion-like particles. And so this is just what I want to point out here on this regime. This is why direct dark matter search experiments can actually probe not only like the MeV, sub-MeV scale in a thermal dark matter world, but all the way to the EV scale if you're transitioning to bosonic dark matter. And this is also here from the same paper from Damik M. They didn't probe the axion-like particles, just the dark photon, or sometimes also called hidden photon. This is more the European word for it. And you can see obviously also they can go down to the silicon band gap, and they are superseding the current bounds that there are. But the one thing I want to point out here, going back to this picture, I said before, this is, since it is basically like the photoelectric effect, it scales to the photoelectric cross-section. This is telling you that, going back to, just really standard model physics, this is the photoelectric cross-section for germanium. And we know that this is all data that has been collected in a huge amount of effort by a former postdoc of mine. And there's a huge amount of data. And then you see here, okay, data, this is where the temperature dependence actually comes in, because the gap energy depends also a little bit on the temperature that you are operating. And then here's some uncertainties, but the key point is really, and this is way less about the details, is that above a certain energy, the photoelectric cross-section really drops, and it scales. So the photoelectric cross-section, scales with the 1 over the third power of the photon energy, so it really drops significantly. And this means if the rate scales with the photoelectric cross-section, the predicted rate scales with the same power, so it really drops. So the sensitivity is not really the strongest anymore. And then if you go back to really standard model photon interactions 101, so the one thing that bachelor students are always ask when photons enter matter, what are the typical interactions they do at what energy scale? Then you are hopefully able to answer that, below about the MeV range, we are in the photoelectric effect regime. And then if you go to higher energies, the Compton effect dominates. And if you go to even higher energy, you're ending up in pair production. Now, if we transition now to the dark boson, so first of all, the moment we get actually to a mass where pair production is possible, then we don't have a good dark matter candidate anymore. So say the dark photon was heavier than twice the electron mass, then it had actually a decay channel. So a dark photon could decay in electron E plus E minus, and it would not be here anymore. So the dark photon is only a good candidate for halo, for relic dark matter, if its lifetime is long enough to survive until today. So it must be actually lighter than twice the electron mass, not decay away. But there's still this regime where the Compton effect dominates. And so this is maybe something where, yeah, I'm probably using this as a pause here. Just saying that depending on, so this again, xenon, germanium, silicon, and then if you look at the different masses, you really have a big difference in so this is, yeah, it depends, right? Where the domination of one effect over the other happens, this also depends on the size of your, or the charge of your nucleus. So basically you're seeing here for xenon, the transition happens later compared to germanium or silicon. And then when looking into germanium a little bit more, this is saying at this energy, so at about 200 kV, the Compton scattering is dominating and by up to 2 orders of magnitude. So at least in this regime, you may want to ask yourself, why don't we just also not only consider dark absorption, but consider dark Compton scattering? Yeah, and I think I pause here because after all, I have another lecture after lunch. Yeah, I think I will pause here, and thanks for your attention. Very good. Yeah, this one. So I have the question to students and the probability theories here maybe. So for dark photons, the cross section is maybe it's the other way around with a mass, and for the other one with a inverse of the mass. But maybe Alex is up and down. Ah, right. So sorry. Yes. Yeah. This one. Yeah. 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 But why, one to the mass and one to the in the rate. It's a homework. Yeah, it's homework. It's hard. You need to. Yeah. There's a reason for both stay or not. Yes. Yeah. 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 Okay, also has some importance in terms of both actually why they are both the ultralight dark matter candidates. Because of it really is, I think, very much related kind of why they are allowed to be light, well, for example, scalars are not allowed to be light on the opposite side. We use scalars that are light, but we need a lot of gears to work behind the scenes to keep them light. While axion particles and dark photons are naturally able to be light, and it's very much related to that scale. Yeah. I knew that you wanted to go to that. It's great. So when you said go back to the, I knew. Very good. Yeah. Yes. When you look at the electron capture now, so in them they're claiming that for electron capture and even also for double electron capture, because the electrons are closer to the nucleus, you have higher coordination, reduced charge yield, and we are trying to kind of reproduce it. Mm-hmm. So
looking, seeing this and knowing that in the menu you have a much better what the charge did, I'm wondering whether there's some sign that you would have to use charge in the store. If you just plug like.
Yeah, if you're basically trying to get the branching ratio compared, or.
You have PR, like beta,
Mm-hmm.
then you have PR. And if you look at let's say, charge versus phonon, of course you need the iLib. So
Mm-hmm.
would you see for these PRs coming from electron capture, that they kind of not into your NR band, because in this case the bands are really separated, but kind of leaking below the PR band. So in general, because the bands are not so separated, they leak. That's what SDCs, we don't see that. So that's why it's kind of in an endpoint, right? I don't see SDCs that.
I don't know of any discussion or even study in that direction. Yeah. No. Yeah, I don't know if, so I know that in the time when I was there was no study in this direction whatsoever. But that is not to say that the effect is not there. I just don't know of anyone who has studied it. Yeah. Yeah. Interesting.